Emil?
Yes, Andreas, thank you so much for the very interesting talk and while opening up this possibility of exploring these complex frequencies. So how do you exactly manipulate these sources? Is it difficult? Do you have good control over these signals?
Yeah, I mean, for these acoustic experiments, is actually almost trivial. Basically, because the decay rates are so smaller in the hundreds of hertz, so we can control them very easily with basically electronic structure. Even at the radio frequencies, it's pretty straightforward. We have a really good arbitrary waveform generator in our lab that can go up to 67 gigahertz. So there is no actual problem for manipulating this type of decay rates or growth rates to modulate the amplitude of a signal with a given carrier. In optics, it can get more complicated. You need to tailor well the slow light enough. Yeah.
So if you can tell us, this profile is finite and then repeated in time. How many typical oscillations you need to have in one of these range?
Yeah, that's a great question. And by the way, I do not have a mathematical formula to tell you how we guarantee that we reach quasi-steady state. I can tell you that, of course, we optimize our structure to make sure that we reach quasi-steady state. And in all these situations, in all these geometries I showed you, that what we found is that it helps a lot to operate near the real frequency axis. What this means is that the quality factors are large. So typically, you need a lot of oscillations. If you want to make it work with 2-3 oscillations, it will never work because you are too far from it. The quality factor is too low. But these structures have quality factors at least in the range of 20, if not more. So at least 20 oscillations in each of these cycles. Because you need to let the system, you will have always a transient at the beginning, right? By the way, in sense of this, in the first paper, this is a PRL from a couple of years ago, in which we introduced the concept of virtual gain. There we demonstrated the PT symmetry based on this principle. So in which we show that you can take a completely passive structure and induce gain in one part of it using this complex frequency and actually get PT symmetric responses. What we did there was to actually find an optimal strategy for excitation to minimize the transient. That's also something you can do. So as I was telling you before, what we do, I mean, there was a very good question before in which you asked, what are you, Misha Lapin asked this, what are you doing before you start decaying or growing? That can affect the transient. So if you choose the right waveform before to minimize the transient, then you need less. And in fact, if you read that PRL, we actually show that you can have zero transient. You can prepare the system with initial excitation to actually completely make zero the transient. As soon as you start decaying, the system responds at that frequency. But this is all very well prepared, like carefully designed to make this happen. We have multiple parts to do that. And it's not, depending on the application, it may not be practical. But indeed, this will never work for too few oscillations.
Thank you.
Thank you. Great question.
Any more questions, guys? Come on.
No.
Yep.
I have a question. Can you hear me?
Yes.
Yeah, sure.
Yes. And Professor Alù, I have a question. And I remember you showed the experimental to achieve the acoustic metamaterials. And I my question is if it's possible to achieve the higher frequency like gigahertz or terahertz.
For acoustics or for electromagnetics?
You like this figure, you image a smile as picture.
This one. Yeah, this one we are actually doing the experiments now in optics. They are ongoing, and we're targeting a few applications, not necessarily the super lens, but some other applications. So the trick in optics is that if you, for instance, let's take the original idea of John Pendry of using a thin layer of silver. For that super lens, the quality factor is too low to make this work, because silver will work at a range of frequencies that is indivisible. So the carrier frequency is hundreds of terahertz. And if you have a quality factor, let's say of 10, you need to modulate your signal at tens of terahertz. And I don't know any way you can do it with that speed and that decay in amplitude. So what we are doing is to tailor this for high Q cavities. So we can build in our lab. Actually, we have two talented postdocs, Xuefeng Zhang and Yuan Chen, that can build these microspheres or toroidal resonators that can have quality factors in the range of 10 to the 8, 10 to the 7, 10 to the 8. And in that case, the light is so slowed down that you don't need to decay that fast. You can decay in the range of gigahertz. And that's what we're targeting. So as you can imagine, you can do a lot of non-emission physics with this type of responses, because you are accessing, you can control the non-hermeticity, the effective, it's like a virtual non-hermeticity of your signal. So we are doing these experiments in optics at the moment, and they are doable, at least for some applications, but you need enough quality factors. For this down the topic below of these elastic waves, I do feel that this can be pushed to the gigahertz range for surface acoustic waves. But of course, this would imply microstructuring. These are 3D printed microscopic structures. You saw the size. So that's why this typically operate at the lower frequencies in our 3D laser vibrometer reaches 25 megahertz. So that's the maximum we could measure with our setup. But I don't see a problem in pushing even higher frequencies if you go to microstructure, nanostructured metamaterials.
Yes, I see. Thank you. Thank you, answer.
Andrea, is there any specific role played by exceptional points in your super lens?
Not for the super lens, but as I said, we have this paper in PRL from, I think it's 1 or 2 years ago, when we introduced virtual gain, and there we show that you can get PT symmetry, exceptional points, you can do all of this, and as you know, this type of structures, this type of phenomena require non-hermeticity, and here we control non-hermeticity through the complex frequency excitation. But for the super lens itself, there is no exceptional point. It's we're really operating very close to what John Pendry originally proposed, but we're just removing that constraint of loss by choosing the decay. But it's basically a very similar phenomenon.
Okay, great. Any more questions, guys? It's a unique opportunity to, you know.
I will be around. You know how to reach me.
Okay. So.
Thank you for inviting me. By the way, also, as I mentioned, I think Simon Yves would be a great speaker for this series. Can tell you more about these experiments. He's amazing, actually, with retrieving.
Speaking of the twisted bilayer graphene,
yeah.
Is there any relation between these and quasi-crystals?
Absolutely, absolutely. Yeah, great question. Yeah, these moire patterns intrinsically are quasi-crystal structures. And in fact, I can tell you that we spent a lot of time, especially for this first paper, in even retrieving even simulating these structures is very complicated because there is no periodicity. And there are a lot of tricks to actually retrieve the right Venn diagrams or defining a Venn diagram. I mean, this, by the way, have been already solved. There are a lot of great community, we had a lot of fun reading this literature on quasi-crystals to actually set up properly and define the Venn diagrams for these systems and efficiently simulating these structures. There are a lot of very nice tricks in the literature. We discussed a little bit in this paper, but yes, all these structures are essentially quasi-crystals for all non-trivial angles. Okay,
excellent. Guys, this was our first webinar of 2022-2023, and we were really happy to have Andrea to start this new webinar series. Well, you know, welcome back everyone on board, and please look up our website regularly for infos on, you know, postdoc positions available, new conferences, and so on.
And we have several openings ourselves, by the way.
Oh, so please take this opportunity. Come on, Andrea.
Yeah, please let me know if you have if you're interested in PhD programs or postdocs. And and thanks, by the way, Sebastian, Bogdan, and Mohammed for inviting. And yes, I'm very happy to be part of this community and look forward to more interactions. Also, for the senior people like you guys, come visit now that COVID is
definitely, and we really look forward, you know, to meeting everyone next year in Crete.
Absolutely,
yeah, this would be wonderful. Okay, great, guys. So see you next week.
Bye. Bye bye.
Stay safe.
Thank you, Andrea. It was a real pleasure.
Thank you.
Bye bye.
See you next week.
Okay.